Okay, hello class. Before we proceed to the flow sheeting by using the simulation tool, I will summarize all the topic that we have learned previously, especially relate to the phase equilibrium, because we gonna apply or we can also solve the problem related to the uh, okay, we also can solve the problem related to the phase equilibria or specifically on the vapor liquid equilibria using a simulation tool. But I will try to summarize all information. I will try to summarize this topic first. Okay, previously we have differentiate between the ideal and non-ideal condition, which for the non-ideal condition, it operates at higher pressure and the okay, previously we have differentiate between the ideal and non-ideal solution or to the real and also the ideal condition. Okay, for the ideal condition, it operates at a lower pressure, which the okay, hello class. We gonna hello class. Before we proceed to the flow sheeting by using a simulation tool, I will summarize the topic relates to the phase equilibria or we have. Okay, hello class. Hello class. Before we proceed to the flow sheeting by using a simulation tool, I will summarize the topic related to the phase equilibrium or specifically about the vapor phase okay, or specifically relate to the vapor liquid equilibria that we have learned previously. Okay, previously we have differentiate between the real and ideal condition. Okay, for the ideal condition, we do not consider on the interaction among the species since it operates at low pressure or low temperature. But for a non-ideal condition, the interaction among the species has been taken into account. Okay, the Rod's law are adequate for many purposes, but it has limitation to operate at low pressure. To overcome this limitation or to apply the solution in the real condition, especially related to the non-ideal condition, we have been introduced to the modified Rod's law or by introducing the activity coefficient into the system. Okay, the activity coefficient is the properties that can differentiate between the ideal and non-ideal solution by introducing the interaction among the species in the system. Okay, in the for the Rod's law, we have the vapor phase to the liquid equal to the liquid phase. But for the modified Rod's law, the liquid phase has been introduced or the interaction among the species has been introduced into the system. So the modified Rod's law is mimics to the real or can be applied to the non-ideal condition. And the next equation we have learned about the equation of state. Okay, the equation of state can be applied to whether example to determine the activity the fugacity the equation of state can be applied to determine example the fugacity coefficient of the P here. Okay, the fugacity. Okay, the another equation can be applied is by using the equation of state. Or we have the benchmark on the value of pressure if we have higher than 15 bar and lower than 15 bar. So we can select the method whether by using the Lee-Kessler or virial equation to determine another properties that differentiate for the non-ideal conditions such as the fugacity coefficient. Okay, the fugacity is the properties that introduced into the system to discuss about the composition in the system. Okay, the fugacity coefficient is equal to the ratio of the fugacity of the species in the solution to its vapor pressure. But for the when we specify on the phases, example for the vapor and also for the liquid, the vapor fugacity of the vapor equal to the fugacity of the species in the, or the fugacity of the species in the vapor is equal to the fugacity of the species in the liquid. So when replace this expression, which is based on the vapor phase, so we can obtain the fugacity in the of the species in the liquid equal to the fugacity of the species in the vapor. And in either solution, which the pressure is lower than 1 bar, the fugacity coefficient is equal to 1. So we can have another expression, or this expression can be obtained at ideal condition of lower pressure. In summary, so the fugacity of the species in the liquid or in the vapor equal to the fugacity, or equal to the at infinite dilution. So the fugacity of the species in liquid or the vapor equal to the saturation pressure, or based on the composition. So it can be a pure species. Example, in the system, we have the ethanolic solution, ethanol plus the water. So for the pure species and for the pure species of the ethanol, that means we're gonna have S1 equal to 1. So this is referred to the pure species of the ethanol into the system. And then the next is the activity coefficient also has been introduced to describe the interaction among the species in the system. So for the fugacity, or for the activity coefficient, we have the ratio of the fugacity of the species in the solution over to its liquid phases. Previously, for the fugacity coefficient, it relates to the vapor phases, but for the activity coefficient, it relates to the liquid phases, or denotes by S. So for the fuga, or previously the fugacity coefficient is introduced to describe the correlation in the vapor phases, but for the liquid phases, the activity coefficient has been introduced, or the activity coefficient equal to the fugacity of the species in the solution over to the fugacity on its liquid phases, or it can be the fugacity of the species in the solution over the fugacity in ideal condition, or it can be described by the Lewis-Arrhenius law, which at the same temperature, pressure, and composition. So replacing this fugacity coefficient to the Roth's law, and we introduced the and this expression is equivalent to the modified Roth's law. So we can obtain the both fugacity for ideal and both fugacity in actual and ideal solution can be replaced by Roth's law. So this is the can be. Kerja abang dek surah solat. Abang ni sekarang nak siap dah. The fugacity of both fugacity in the ideal and also the fugacity in the solution can be replaced by the modified Roth's law. So the activity coefficient equal to the vapor phases to the liquid phases. So the next properties to differentiate on the ideal and non-ideal solution by using the next property to differentiate between the ideal and real condition is based on the activity coefficient. The activity coefficient has been introduced once we consider the interaction among the species. So the activity coefficient is equal to the fugacity of the species I in the solution over to its liquid phase, or the fugacity of the species I in the solution over to its ideal, or the fugacity in ideal condition. Okay, this expression is equivalent to the modified Roth's law, which we can replace the fugacity in ideal to the ideal, which we can replace the fugacity of the species in the solution to its composition in the vapor phases, and also the ideal solution is equal to its saturation pressure. So this is the another expression that we can use, or known as the modified Roth's law, to calculate the activity coefficient. The fugacity can be divided into the fugacity has we also have learned about the fugacity in the pure species, mixture gases, and also the solution of liquid. Okay, for the pure species, or the ideal gas, is equivalent to the pressure, or the fugacity coefficient equal to 1. Okay, for the mixture of gas, so we consider on the composition in the gas phases. And for the solution, okay, the solution, that means we have the ideal of the fugacity in the solution equal to the composition in the liquid phases, or we can use this expression or to express the in the ideal solution. Okay, next, how can we obtain the gamma? And also the gamma is expressed by the activity coefficient, and the phi is expressed by the fugacity coefficient. So we can correlate this expression to give another expression, or in a non-ideal condition, in the gas phase, the fugacity as the or we can correlate between the fugacity coefficient and activity coefficient if we have the non-ideal condition for both gas and also the liquid phases, to investigate the interaction among the species with the activity, which the fugacity coefficient can be determined by using this factor of Poynting factor, or the fugacity coefficient can be determined using this expression, or the fugacity of the species in the solution over to its saturation exponent, the Poynting factor. And if the Poynting factor is equal to 0, that means we have the higher pressure compared to its saturation pressure, we can get the fugacity coefficient, or replace into this expression. And for the activity coefficient, we can obtain from the modified Roth's law. Okay, how about to compare with this expression to the Roth's law? So for the Roth's law, that means we operate at ideal condition, or the fugacity coefficient is equal to 1. So in ideal solution, the activity coefficient is equal to 1. So eventually we can get the Roth's law, or the okay, from this expression that we introduce the interaction of the species in the vapor phase by introducing the fugacity coefficient, and also the interaction of the species in the liquid phase by introducing the activity coefficient. In the ideal condition, or for the gas phases, so the fugacity coefficient is equal to 1. So we can have another expression known as the modified Roth's law. And then if we have the ideal solution with the which the activity coefficient is equal to 1, we can obtain the Roth's law, or the vapor phases equal to the liquid phase by do not considering any interaction in any, by do not consider the interaction in any phases. Okay, the fugacity coefficient can be obtained by using the true variable equation through the true variable coefficient. Okay, this is the expression or to express the okay. Okay, how can we obtain the fugacity coefficient? The fugacity or denoted by phi here can be determined by using this expression or relate to the pointing factor. In ideal condition, the pointing factor is near to 0. So we can express the fugacity coefficient equal to the ratio of the fugacity of the species in the solution to its saturation pressure. So we can obtain both expression using this equation for the fugacity of the species in the solution and also this fugacity coefficient in the saturation. So these these properties can be these properties of the beta, the property the constant of the B and also the delta here is expressed by how can we obtain the fugacity coefficient or denotes by phi here? Okay, the phi or the fugacity coefficient equal to the ratio of the fugacity coefficient in species. Okay, how can we obtain the phi or the fugacity coefficient from the V? Okay, the fugacity, how can we obtain the fugacity coefficient from this expression? Okay, from this expression, we need to obtain the fugacity of the species in the solution and fugacity in the saturation. Or if we have the pointing factor is equal to 0, that means we have a higher pressure compared its saturation pressure. So by considering the pointing factor is equal to 0, the fugacity coefficient equal to the ratio of the fugacity is of the species I in the solution to its saturation condition. So the fugacity of the species I in the solution equal to this expression, and the saturation can be obtained using this expression, which B and also the rest properties is described by the variable coefficient. So we can obtain the fugacity. Example, in the solution we have two species, so we should obtain the fugacity coefficient for the species 1 and 2 using this expression. All the value of B and also the gamma we can the value of this constant can be obtained from the variable equation. Okay, how about to determine the fugacity? Okay, this is summary. How can we obtain the fugacity coefficient? By using the equation of state. It based on the, we may refer to the value of pressure. If P higher than 15 bar, we can use the de Kessler method or refer to the table. But if P is less than 15 bar, we may use the variable equation. So this is the detailed step that you can obtain from either by using variable coefficient or the de Kessler that we have learned previously. Okay, the detailed expression on the correlation for the non-ideal condition in the vapor phase and in the liquid phase, okay, by introducing the fugacity coefficient in the vapor phase to consider the interaction among the species in the vapor phase, and for the liquid phases, the fugacity, and then for the liquid phases, the activity coefficient is introduced, which the first for the last term here is the term that expressed on the vapor phases. The fugacity coefficient can be defined either by using the equation. Okay, in a real solution, in a real condition, which the interaction of the species in gas phases and also in liquid phases is considered by introduce the fugacity coefficient in the gas phase to describe the interaction of the species, and also in the liquid phase we introduce the activity coefficient to describe the interaction among the liquid phases. Okay, for the gas phases, we can obtain the fugacity coefficient by using the equation of state. Using this following equation, it depends on the application, whether the process is hydrocarbon or whether the process in a vapor phase at higher pressure. So you may describe the fugacity coefficient using the equation of state. But for the activity coefficient, or we consider the interaction among the species in liquid phase, we can describe this activity coefficient using the model of excess Gibbs energy, either by using the Margulis equation, the Van Laar that we have learned previously, or the local composition model, either by using Wilson and RTL unique or unified model. The fugacity coefficient and activity coefficient is the function of the temperature, pressure, and its composition. It depends on the phase, and the saturation pressure, the function is based on the temperature. So to determine the calculation, or to perform the calculation based on the dew and bubble point, so we may introduce the okay, at the moderate pressure, the gamma of V approach to the VLES is approached with the activity coefficient is assumed independent with the pressure. Okay, by rearrange stop awak ni. Muhammad Lam. Okay, all the calculation made by gamma and also phi here, formulation require iteration due to its complex functionality. Okay, the gamma and phi here can be a function of the temperature, pressure, and its composition, which for the saturation pressure is function on the temperature, which we can obtain the saturation pressure using an Anton equation. Okay, at moderate pressure, the gamma and also P approach to VLE is approached with the activity coefficient is assumed independent of the pressure. Okay, by rearrange the equation to obtain the composition, whether in gas or liquid phase, so we can obtain the composition using this expression. Okay, this equation, the equation 14.1 is example for the gas phases. We introduced the fugacity coefficient into the expression, or in gas phases the fugacity coefficient to the pressure equal to the, in liquid phases we introduced the activity coefficient, or SI, the activity coefficient, and PI saturation. Okay, the PI saturation is function of temperature. And finally, we can obtain the composition by using this expression. And then by submission of the example in the vapor phases, the submission of the composition is equal to 1. So we can have another expression, or in a liquid phases, the sum total composition in the liquid phases is equal to 1, and we can get another expression. So to solve the pressure, to obtain the pressure, we can replace it or rearrange this expression to obtain this a new expression of pressure in the liquid phases equal to the summation of the composition in the liquid to its activity coefficient and its saturation pressure over the fugacity coefficient, or in the vapor phases, it turns to this expression, or P equal to 1 over summation of the composition in the vapor times its fugacity coefficient over to the activity coefficient times the saturation pressure. Okay, for the case relate to the bulk temperature and due temperature, that's mean for the bulk temperature, we obtain the, we need to find the composition. Okay, for the cases of the bulk temperature and for the cases of the bulk temperature and due temperature, that means we need to determine the temperature. The temperature is not given to us, so we need to apply the procedure of trial and error by comparing the calculated and gas temperature. So rearrange the Anton equation so we can obtain the saturation temperature, and then inserting the value that we obtain here to give the calculated temperature, and comparing with between the gas temperature and calculated temperature to finally give us the value of temperature. These are the summary in calculating the bulk P. Bulk P, that's mean the composition in the liquid is given and we need to find the pressure. So by using this, okay, since the pressure, we need to find it. Okay, for the bulk P calculation, that's mean the composition of X is given, or the in liquid phase is given, and the pressure, we need to find the pressure. So the temperature also will be given here. Okay, so we can evaluate the saturation pressure using the Anton equation. And then after that, we can calculate the value of P. So P equal to SI, PI saturation, or the summation of SI, PI saturation. And then finally, we can obtain the value or the composition in the liquid phase using the modified Ross law. And also we can evaluate the phi by using this equation, by using the expression or the, okay, finally we can evaluate the value of phi from the equation here. So this is the okay, finally, we can obtain the composition in liquid. Okay, finally, we can obtain the composition of the vapor phases by using the correlation of YI, the phi, P equal to SI, the activity coefficient, and PI saturation. Okay, rearrange, we can obtain the composition in the liquid phase. And to obtain to evaluate the phi here, we can use the equation of the variable. And then finally, we can calculate the pressure. And then comparing the pressure between both calculated here. So if the lower than the, or it has the lower different, or if the delta P is lower than the, if delta P has a lower error, or if delta P has a lower tolerance, so we may finalize the value of pressure and also the composition. Otherwise, we need to reiterate the process. Okay, for the due temperature, due, that's mean with the composition of the, we need to, okay, due that, okay, for the due P calculation, that mean we, okay, for due P calculation, that mean the composition of the vapor is okay, for the due P calculation, that means the composition in the vapor is okay, for the due P calculation, that means we need to find the composition in vapor, and the P is given. So if the P is given, that means we need to find the temperature. What is the temperature? So by using the Anton equation, so we may calculate the, okay, for due P calculation, that's mean the composition in the vapor phase should be defined, and then P, what is the, okay, for due P calculation, that means we should define the composition in the vapor phase, and then we also need to find the pressure. Okay, for the due P calculation, the composition in the vapor is given, and we need to find the pressure in the system. So since the temperature is given, we can obtain the pressure by using the Anton equation to obtain the saturation pressure. And then after that, we may calculate the pressure using this. And we may calculate the pressure using the P equal to, since the vapor phases is given, so you may use the correlation of the 1 over summation of Y I d phi I over P1 saturation. Okay, for due P calculation, that's meaning we need to find. Okay, for due P calculation, that means the composition in vapor is given. We need to find the pressure. Since we need to find the pressure, we may determine the saturation pressure using Anton equation. And then the pressure is calculated from the P equal to 1 over summation of the okay, for bulk P calculation, that's meaning composition in liquid is given, and we need to find the value of the pressure. Okay, the saturation pressure can obtain from the Anton equation, and the composition in the vapor phase can be obtained from the modified or from the and the activity coefficient can be obtained from the activity model by using Van Laar or Margus equation. And then after that, we may calculate the value of pressure. Okay, the general equation is the in the vapor phase, we introduce the fugacity coefficient to the pressure equal to the liquid phases. We have the composition to the activity coefficient and P1 saturation. Okay, to obtain the value of P here, we can rearrange P equal to SI activity coefficient, PI saturation over YI gamma or Phi saturation. So the P here is obtained from the, so from this expression, we need to determine the, evaluate the fugacity coefficient and also the composition in the vapor phases. To calculate the composition, we may use the equation of, we may use the equation of Yi equal to Si, the activity coefficient, over Pi gamma I. So we may calculate this and then evaluate the phi here. So we may evaluate using the Equilibria equation from previously, from the previous equation. And then we may determine the fugacity coefficient using the virial equation and evaluate this. We may evaluate the fugacity coefficient using the virial equation. And then after that, we may calculate the value of P using this equation. And then if we obtain the delta P from the first calculated to the next calculated, if higher tolerance, so we may proceed with the iteration. Otherwise, we may finalize the value of pressure and also the composition in vapor phase. For the DUP calculation, that's mean we have the information on the composition in the vapor phase and we need to find the pressure. So since we need to find the pressure, we may obtain the saturation pressure. Since the temperature is given, we may obtain the saturation pressure from the Anton equation. And then after that, we may calculate the value of P from the equation here. 1411 is the, we may calculate the pressure using the equation of, since the vapor phases is given, so 1 over the summation of the vapor to the fugacity coefficient over the activity coefficient and P1 saturation. So calculate the composition of the X using the equation here or the virial. And then calculate the composition in the liquid phase using the expression of the, because we have the general equation is the the general equation in non-ideal condition is the interaction in the vapor phases by introduce the fugacity coefficient P equal to Si gamma I Pi saturation. So the composition in the SSI equal to composition in the vapor, the fugacity coefficient P over gamma I Pi saturation. And then we can evaluate the gamma or the activity coefficient from this equation. And then after that, we may calculate or recalculate the value of pressure inserting into this equation to evaluate the value of gamma. And then after that, we may calculate the liquid composition and then normalize the composition by using this expression. And then finally, we can obtain the activity coefficient or and then after that we need to evaluate the activity coefficient, and if the difference of the activity coefficient is less than H tolerant, we may proceed to calculate the value of P using this equation. And then if the delta P also has lower than tolerance, so we may finalize the value of P and also the composition in the liquid. Otherwise, we need to perform the iteration from the first start. For the bulk T calculation, so for the bulk T, since the temperature, we need to find the temperature, so we can use the Anton equation to obtain the value of saturation temperature. Okay, for the bulk T, that's meaning the composition in the liquid is given and we need to find the temperature. Okay, and then by that we can set all the fugacity coefficient is equal to 1 and we can obtain the saturation temperature using Anton equation or by rearrange the Anton equation. And then we may calculate the temperature using this expression of summability relation. And then after that, we can define the we can evaluate the saturation pressure and also the gamma. And then inserting into this equation to obtain the saturation pressure, and then finally evaluate the saturation pressure and calculate all this value. First the composition in the vapor phases, and then we can evaluate the fugacity coefficient. Okay, ideally the general equation is based on the correlation in the vapor phases by introduce the fugacity coefficient P equal to the correlation in the liquid phases by introduce the activity coefficient. So evaluate the phi here using this equation, and then finally we can calculate the saturation pressure by using this equation. So you may refer to the equation here. Okay, these are the list of the equation to be used or applied in calculating either the bulk of dew. And then if the tolerance is lower than the example for the delta T is if the tolerance is lower, so we may finalize the temperature and also the composition in the vapor phase. Otherwise, we need to perform the iteration. Okay, for the dew, that's mean the composition in vapor is given, so we need to find the temperature. So since we need to find the temperature, the pressure is given. So we may evaluate the saturation temperature. Okay, to evaluate the saturation temperature, or we can okay, for the dew T calculation, dew that's mean the composition in vapor is given, so we need to find the temperature. Okay, since we need to find the temperature, the pressure, and also the composition in the vapor is given. Okay, by setting the fugacity coefficient is equal to 1 and the gamma equal to 1, so we can calculate the saturation temperature using or rearrange the Anton equation, and the temperature is obtained from this summability relation. And then after that, we may evaluate the saturation pressure, and then the saturation pressure for each species also can be evaluated. And then after that, we may calculate the temperature and comparing the temperature from the calculated temperature. And then after that, we may evaluate the saturation pressure, the fugacity coefficient, and calculate the composition in liquid using this equation, or the equation of the, you may rearrange the general equation of S, or the YI, the phi I, P equal to SI, the gamma I, PI saturation. Okay, to obtain the composition in the liquid, so SI equal to gamma I to obtain the composition in the of the species in the liquid phase. So SI equal to YI phi I P over S gamma I PI saturation. So we can calculate the composition in the liquid phase using this equation, and then evaluate the gamma and recalculate the saturation pressure. And then after that, we may evaluate the saturation pressure and also the fugacity coefficient. Okay, we may evaluate the saturation pressure and also the fugacity coefficient using the virial equation or equation 14.6. Okay, the equation 14.6 is given here. Okay, this is the equation 14.6 using the virial coefficient. Okay, and then after that, we may calculate the composition from this equation and then normalize the composition using using this expression, and then we may evaluate the fugacity coefficient. And then calculate the composition in the liquid phases using this equation or virial equation, and then we may evaluate the composition in the liquid using this equation 14.9, and then after that normalize the composition based on this expression, and then finally we may evaluate the fugacity. Finally we may evaluate the activity coefficient. If the activity or difference, if the different activity coefficient is less than tolerance, we may calculate the saturation pressure and also the temperature. And then after that, we may recalculate the calculate the difference of the temperature by define its tolerance. If the tolerance is lower, so we may finalize the temperature and also the composition in the liquid. Okay, for the flash calculation, the other way to obtain the gamma and phi formulation for the VLE by using this expression. So the composition of the liquid phases and vapor phases also can be obtained from the flash calculation. So we can perform this flash calculation by performing the Okay, the other method is using the flash calculation, which the flash calculation can be applied using the gamma phi formulation of VLE, but the calculation is more complex. The primary equation that we have learned previously in obtaining composition in the vapor using this expression with Ki, we may obtain from the d piston or the Okay, previously we have learned the K value can be obtained from the D piston. It depends on the if the system is related to the light hydrocarbon, and C is the composition in the feed stream, and we have the vapor and also its composition from the D piston. Okay, the flash calculation also can relate to apply the gamma and also phi formulation in VLE, but the calculation is become more complex. However, the primary equation is remain the same. So in determining the composition in the vapor phase, we may use this expression with the K value can be obtained from the D piston if the system is related to the light hydrocarbon. And another phases is the liquid phases can also be used using this expression by perform the rearrangement on this expression, or we know that the composition in the liquid equal to the composition in the vapor over the Ki value. And then after that, we may consider the submission of the total submission of each composition in each phases is equal to 1. So we can apply this correlation and the expression or the flow rate. Okay, the flash calculation also. Okay, flash calculation also can be applied in using the Okay, we can also apply the calculation using gamma phi formulation for BLE. However, the calculation is more complex. Okay, primarily the question is for the vapor and also the liquid phase is expressed in this expression, and then both side of the mole fraction must equal to the unity or the summation of the vapor and liquid phase is equal to 1. And then after that, we may introduce into this expression by the difference of the. Okay, we may also apply the gamma phi formulation to the flash calculation in solving the problem related to the VLE or phase equilibrium. However, the calculation become more complex. However, the expression is remain the same, which the composition in the vapor phase equal to the Z is the composition of overall times the K is the factor can be obtained from the D if relate to the light hydrocarbon system, and using this expression with Ki equal to Yi over Si. So rearrange this, we can obtain the liquid phases using this expression. And then by perform the summation of this each composition in each phases equal to 1, so we can obtain this expression. And then rearrange once F equal to 0, so we can okay, by applying this. Okay, by applying the summation of each phases is equal to 1, so we can obtain the flow in the feed stream is equal to 0 for the vapor phase, and this is expression for the liquid phases. So since the difference of the vapor phase to the liquid phases equal to F, so we may obtain another expression, and by differentiate this expression, so it can give another equation or equation 14.20, and using this expression, so Ki equal to this is for the expression in the liquid phase. And the expression of the ratio of the vapor to liquid phase or denoted by Ki can be replaced by using this, or Y equal to the introduce the gamma or from the expression of the Yi, the phi P equal to Si activity coefficient and Pi saturation. So using this ratio, so we can replace it to this expression, which from this expression, if the Ki is the equilibrium ratio or K, okay, from this expression, we can measure the tendency to favor the vapor phases, which higher Ki. If we have higher Ki, that means we have higher concentration in vapor phases. Okay, this the summary method for the pressure temperature. Okay, these are the summary method or the block diagram for the pressure temperature flash calculation. So for the temperature pressure flash calculation, so the temperature, pressure, and also the mole fraction is constant. Okay, for the DUP calculation, so we can apply this correlation of the due, that's mean the given composition in the vapor phases, which the vapor phases equal to its overall composition. And for the bulk P calculation, bulk, that's mean the liquid phases is given and the composition in the liquid equal to its overall. So we may check whether the P due is lower or within this. We may check whether the pressure within this okay, we may restrict the rules. Okay, if the dew point, okay, these are the restrictions to be considered if the dew pressure is less than pressure and less is the bulk pressure. So we may estimate the gamma or the fugacity, gamma and the okay, to proceed with the solution, we may check on this restriction whether the dew pressure is less than pressure and less is the bulk pressure. If the restriction is followed, we may estimate the fugacity coefficient, activity coefficient, and also the vapor, the value of vapor. If not, we may stop the process. And then after we estimate these values, we may evaluate the Ki. Ki equal to Yi over Si, or Yi is the expression on the phi I P. Or for the Yi over. And then after that, we may evaluate the Ki value. Ki equal to Yi over Si, or it expressed by the gamma I, Pi saturation over Pi, Pi. So we may use this correlation to evaluate the Ki. And then after that, we may evaluate the F and also the difference of the flow using this. And then after that, we may evaluate the fit and also the different fit using this equation as listed here. And then after that, we may re-evaluate the composition in the liquid phases and also the gamma as well as the fugacity coefficient using this equation 14.16 and 14.6. And then after that, we may consider on its tolerance if the delta V is less than its tolerance, or whether the composition, the different. And then after that, we may evaluate the properties based in tolerance if the delta V or delta S or the delta Y is less than its tolerance. So we may finalize the volume and also its composition. Otherwise, we need to perform another iteration. Okay, in summary, the VLE or flash calculation, we can perform the calculation based on the bulk calculation or dew point calculation and flash calculation. Okay, bulk point, that's mean we, bubble, that's mean we, the composition in the liquid phases is given, so we need to whether find the pressure or temperature. And the dew, that's mean we have. Okay, for the dew, that's mean we obtain the composition in the vapor is given, so we need to whether find the value of pressure or temperature. And then for flash calculation, it's based on the isothermal and adiabatic. Okay, for the isothermal that we have learned based on the balance on the F equal to V plus L. But for the adiabatic, we need to refer on the heat energy in the system. The VLE calculation also can be obtained using the simulation software or UNISIM that we will cover on the next chapter. Okay, first we have this basic features we known as the basis manager environment that consists of the component, fluid package, and hypothetical. Okay, for the component features, we can add the component into the system. And then fluid package, we need to identify what is the fluid package to be used for both fugacity coefficient and also the activity coefficient. Okay, for the fugacity coefficient, we have learned that it relates to the equation of state. And for the fugacity and for the activity coefficient, it relates to the model of Gibbs, such as the Margus equation, the Van Laar equation. So you may use that equation to obtain the activity coefficient. And for the hypothetical features, that means we added another component that are not listed in the system or in the library list. So we introduce another component and we should insert all the properties such as the eccentric factor, the critical pressure, the critical temperature, and etc. And then after that, we may simulate it in the simulation environment, or known as the PFD view. Okay, for the PFD view, it gives us the information on the condition, which we need to specify what is the temperature, pressure, and also the vapor fraction. Okay, for the composition, we should specify the mole and also the mass fraction. And finally, for the properties, is related to the critical values, such as the pressure, the value of the critical pressure, and also the temperature, critical temperature. Okay, to perform this condition and also the composition, before we identify the condition and also the composition, we should perform the material and energy balance that we have learned previously in the previous module. And then this otherwise, the BLE calculation also can be performed by using a simulation tool, either by using UNISIM, the SuperPro design, and etc. Okay, these are the basic manager environment that introduced in the simulation tool. So it consists on the component, fluid package, and hypothetical. Okay, for the component area, we may add it component into these features. And for the fluid package, we can specify the method for the fugacity coefficient and also the activity coefficient. Okay, for the fugacity coefficient or phi can be determined by using the equation of state. And for the activity coefficient, we can determine by using the model Gibbs energy, such as Margus equation, Van Laar equation, or the local model we have learned in briefly about the unique weight and RTL and etc. And the next features in the simulation is the hypothetical. Okay, hypothetical, that means we added another component which are not listed in the library list. Example, in your system, you introduce another component or another species, and then you may add that new or the customer species under the hypothetical features. And then after that, we may simulate the process, or call as this. We may simulate the process under the simulation environment, or it gives us the PFD, process flow diagram view. And in this PFD view, it consists of the condition, composition, and the properties. Or the composition will be the composition required, such as the temperature, pressure, and also the vapor fraction. And for the composition, we should specify the mole, mass fraction, and also the flow rate into each stream. And for the properties, usually it based on the hypothetical, which it relates to the properties such as the critical temperature, critical pressure, and so on for each state, for each component. Okay, we proceed to the condition and composition, which we can obtain this composition by using BLE or flash calculation. So you may specify whether for using the flash calculation, we have PT flash, or for the bubble T. So these are the specific or the detailed condition and composition that we will proceed with. And also we have another bubble pressure, that's meaning the composition in the liquid is given and we need to find the pressure. Du, T, that's mean the composition in vapor is given and we need to find the temperature. Same goes to the pressure. The composition in the vapor is given and we need to find the pressure. Okay, the next topic, we're gonna learn how to apply the flow sheeting relate to the phase equilibrium in the simulation tool. So in summary, you should be able to differentiate between the non-ideal and ideal, which for the non-ideal that's mimic to the real condition. All the interaction in the liquid phase and in the vapor phases is considered. For the vapor phases, we introduce the fugacity coefficient, and for the liquid phases, we introduce the activity coefficient, which the fugacity coefficient can obtain from the equation of state, and the fugacity and also the activity coefficient can be obtained from the model Gibbs energy, or we can obtain the activity coefficient from the modified Ross law in detail. So for the next, we're gonna learn how to hands-on with the UNISIM, or we're gonna learn more on the flow sheeting in the simulation tool. So I'll see you for the next topic. Bye.